Thank you very much. And thank you all for having us here. Can you hear me well in the back? Yes, nodding faces. Good. Thank you, first of all, for inviting us with this short symposium and giving us the opportunity to kick off this great conference with a series of 4 talks on realities, of course, as the theme of the conference befits, but 4 talks about the realities of geometry. So in my talk and the next 3 talks, you will see how geometric concepts that are to a certain extent abstract or in the realm of almost Platonism do get a new sense of reality, a new sensibility by the projects that you will see. And I'm going to start here with 3D printing the geometry of sound to give a new reality to sound. I should say that you're very welcome to tweet from my talk. Here's my Twitter handle. If you're inclined to do so, do that. And I should also say that this is joint work with Ulrich Reitebuch. I will have a reference to a paper of what I'm going to talk about today later on in the talk. As Martin already said, I'm at TU Delft. I'm a trained mathematician. I'm now at the computer science department. And if you look at my use of numbers here, you will see that today is not August 23rd. So it's probably good that I'm not in a mathematics department anymore, but sort of switched to computer science. All right, let me tell you about this project of ours. And this all starts quite a while ago with Ernst Florenz Friedrich Chladni, who published his theory of sound. And in this book that he published, he has an experiment to visualize vibration modes of sound. And the experiment goes like this. He sprinkled some sand on a metal plate, and then he used a violin bow and he struck it in a really steady rhythm. And what's fascinating at this point is that the metal plate is vibrating and the sand pieces are jumping and bumping around, but they're not all falling off. Some of them might, but not all of them are falling off. What actually happens is that they form these intricate patterns here that are already described in Chladni's book. And actually, Chladni wasn't the first to discover that, but he really toured Europe with this show of sprinkling sand and letting the metal plate vibrate and showing off these great figures. So let's spend maybe a slide and try to understand what's happening here. And I try to do this, I don't really have a good notion of the audience, so I try to do this quite visually, and I will have some math for those that really want to see the math. But let's do it visually first, yeah? So sound is a wave, and a wave is traveling in one direction. And imagine this wave traveling through this metal plate of Chladni. At some point, it will hit the end of the metal plate. And what happens is it's reflected and it travels the other way. And now the wave traveling the one way and the wave traveling back, they're hitting each other and they're starting to overlay. So this top blue wave and the bottom red wave coming back, they're overlaying, and you see here in black what happens if they overlay. And this is what we call a standing wave. This wave is not moving left or right anymore. It's right there in place. And there's areas in this black wave that are moving up and down quite a bit here and there. But if you look closely between these hills and valleys that arise, there's points that are actually fixed. They remain. And these are the points where the plate is not actually vibrating. And so if a sand grain is settling in that part of the metal plate, it's not moving anymore. Here's the math. What's interesting here is that we do have 2 really different solutions to this, and we'll come to that on the next slide, because these waves, they can have 2 fundamentally different ways of how they interact with the plate. They can have what we call Dirichlet patterns, where the wave has to be resting at the end of the plate. And we don't really care what's happening in between, but at the end, we will have to have one of these resting nodes. And the other way is what's called von Neumann waves, where again, we don't really care what happens in between, but here at the end of the plate, we will have to have a valley or a mountain peak in this movement. And we will see the difference that this makes in a second. So again, here's the math. You have two different ways how to describe this, one with a sine and one with a cosine solution. But let's look at what happens in 3D now. What happens if we have sound move in a three-dimensional volume, and we're going to pick the sort of easiest volume here, which is a cube. It has three directions. So the one pattern I'd like to point out here in the mathematics is that it's quite regular, that you have these three different terms here, and you basically solve for all their patterns. So that leaves us with a bunch of parameters, A to F, that we can alter, and U, V, and W. So in the following, when I'm going to talk about altering parameters, I'm going to talk about these. Let's look at pictures. The pictures I'd like to show you look somewhat like this. And at this point, I would like to ask Dave and Teresa to maybe already start and hand around a 3D printed version of one parameter set. So hopefully at some point you all get a chance to actually feel it and see and touch the sound. Isn't that lovely? And I'd be really happy if that finds its way back to me at some point. So what I'm going to show you is these cubes. They're filled with surfaces, and these surfaces are the analog to what used to be the lines in Chladni's way of describing this. So now we're talking about surfaces of sand resting in this cube, and they have two sides, a black and blue side and a green and white backside. So we colored them so you can distinguish these. We divide this into small cubes to give them this checkerboard pattern. And here's the backside, green and white, the front side, blue and black. And we should say all this has been rendered with a great tool of POFRay. So if you ever need to make pictures like that, POFRay is your friend. The figure sizes I'm showing here is a bit off to what Chladni did. Chladni had this one plate, and I'm going to show you not one, but actually 8 little cubes. Yeah? So this pattern here repeats 8 times. You see it once here in front, once mirror symmetry to the side, mirror symmetry to the back and here. So you have 4 here, and then you have the same arrangement again mirrored to the bottom. And here you see the difference between these solutions that we had, Dirichlet solutions that have this strong, hard boundaries here because we required the rim of the cube to be a resting place for sand. So the sand forms these real hard walls. Or you could have them orthogonal to the border. So here you have the strong walls, and here you have the corresponding Neumann boundary condition where it's orthogonal to the boundary of the cube. Because we're now talking about sound in 3D, not all these cuts, not all these red parts are actually two-dimensional Chladni figures. We're really delving into new dimension. We're exploring more than what Chladni had because we have these intricate interactions of three-dimensional sound waves. And we can start playing with this. We can start playing with the mathematics, and we can start wandering. We can start a walk through this space of parameters, and we can see how the sound patterns change. So we're not changing the sound, we're changing how we amplify it, how it interacts in these 3 dimensions of the cube. And you get something quite organic, something that's almost breathing. Now we can go on several of these journeys on the parameter space, and we can walk through them, and we can see what different solutions pop up. Some we might like, some we might dislike. but they all have this quite flowing, organic feel to them. Not necessarily the sound moving, but really the sound interacting with each other. And that's what I want to leave you with here. Thank you so much for your attention. Here's the proceedings paper. If you want to look it up, if you want to read it, read about it in more detail. If you have any questions, feel free to shoot me an email or tweet me. Thank you so much.